how to decide which K to pick in K-means clustering. So we're going to be looking at page 245 now and going quickly to 246. And I'm going to shortly pull up the collab. There we go. And I figured out that nobody was able to see anything with my collab being dark, so I've switched it to light. Sorry if it's too bright. There we go. Okay, so basically, if we run the same algorithm, the same data set with two different K clusters, we can choose 3 on the left or 8 on the right. And 3 doesn't do a great job, and neither does 8. 3 kinds of lumps things together, and 8 separates things that should be together. So how do you really decide what number to choose? And Jerome suggests 2 different methods. He does talk a little bit about using the inertias first. And the problem with the inertia is that for the inertia of 3, you calculate a 653. 8 is 118. That 8 is low, but you're still not getting a good you're not getting a good centroid for your clustering, because you're taking too many clusters and breaking up your actual clusters that are here and here. So you can't just rely upon the inertia itself. Same problem that we see in a lot of medical data set evaluation, where you just can't rely upon the ROC or another metric like accuracy de novo. You have to look at different things. So what he suggests instead to do is to do a brute force evaluation of the inertias and see where the inertias kind of bend. He calls it an elbow, and he just runs the inertias from 2 to 8 and plots them, and you get this, where there is an inflection point at 4. So the inflection point at 4, if we plot this out, we'll get a pretty good separation of the different clusters, with the limitation that the 2 clusters here kind of get lumped in together. So that is a quick and dirty way to do it, I believe. The question is, how else can you do it? And he talks about the silhouette score and silhouette plots. So the silhouette score is calculated by taking the difference from intracluster, the mean intracluster difference, and the nearest cluster difference, with the mean nearest cluster difference being subtracted from the intracluster distance, and that is divided by the maximum of the 2. So it's a score that varies between -1 and +1. A coefficient close to +1 means that the instance is completely inside its own cluster and as far away from other clusters as it can get. A coefficient at 0 means it's close to the boundary of a cluster, and then a coefficient of -1 means that there may be a wrong assignment. So it's one of these -1 to 1 scales that you kind of have to be aware of, especially if you're doing comparisons to 0 to 1 scaled metrics. So you have to end up converting and normalizing them. So plotting the silhouette score as a function of K, it's an actual routine in scikit-learn. We're going to pass it our data, and we're going to get out for each of the models that we did, we're going to get a different score. So we plot this score, and we can see that 4 is highest at 0.68 or around there. 5 is decent too, and then other scores are lower. There's not a tremendous range of variation. The lowest is 3 clusters at like 0.575, and 8 about the same compared to 0.69, 0.68 for 4. So he calls this a richer visualization than the elbow plot, and he feels it makes more sense. And then when you plot every instance's silhouette coefficient, sorting it by the cluster that they are assigned to, and the value of the coefficient in the silhouette diagram, you get this kind of cool knife blade diagram here. And I think that the take-home point is that he's setting this line here, and I believe the line, if I recall, is the mean I forget what it is here.
I think it's the mean silhouette coefficient of all the data points.
Sorry, it's the mean silhouette coefficient. So the point, what you are trying to see is you're trying to see a knife diagram that passes that mean. And that is, a goodness of fit or a goodness of clustering, if you will. So take a look at the different plots he has for 3, 4, 5, and 6. So 3, we have 1 knife blade that doesn't meet the mark, 2 knife blades too. 2 of the clusters are okay, but this is insufficient. At 4, we have each of the clusters meeting the mark. 5, each of the clusters meeting the mark. And at 6, we have 2 clusters not meeting the mark. If you were to be a stickler, you could say, well, if you look at 5, it's somewhat better than 4 because the 4 just kind of hits it here and just kind of hits it here, but in 5 they seem to be further over the line. So perhaps 5 is a better choice than 4 on the basis of this diagram. Okay.
Also, the diagram has, it's a little bit funny because the author didn't really take care of properly labeling the axes, and three of the plots have the same x-axis, but the one on the top doesn't. And that threw me off for a while. The one on the top, the x-axis, the point x equals 0 occurs at the left-hand edge of the knives. And so it, the mean silhouette coefficient is somewhat less than 0.6. But if you look at, if you think, if you look without thinking it has the same scale as the other plots, you'll think, oh, it's bigger. It's got a bigger silhouette coefficient than the k equals 5, but that's not the case.
I did not realize that. Okay. Thank you, Joe. All right, so basically this is what he's talking about. Let me just quickly pop into here and make sure that there is not another point that we need to address. No, pretty much those are the 2 points that I wanted to make. So you can either try the elbow technique or you can try the silhouette score and make a knife plot with it to try to get an idea of where you want to put your clusters. So moving on, the clustering so if we take a few of these different clusters, now we have clusters. There's a reasonably well-defined cluster here. This is pretty ill-defined, and this is ill-defined, and particularly the interface between these two is not particularly well-defined. So how, to deal with this, and how are we going to separate them? If you just take lowest inertia, you're not necessarily going to get the best plot. I mean, this inertia is lower than this inertia. The lines, however, that this inertia is drawing are not separating things well. And I think that this is an indication of where Voronoi diagram is pretty useful, because I think most of us would immediately reject this out of hand, but we might be willing to accept this, even though I think.
So it looks like the difference, always asking myself, what's the difference between those two plots, where the one on the left looks pretty good, not too bad, and the one on the right looks horrible. If you look at the code, the difference is that the one on the left was generated by giving it an initial guess that was close to where the centroids really are. Whereas the one on the right, it was not given an initialization, it just was randomly, in other words, that means it will randomly initialize itself, and then it doesn't do very well.
And I think also the number of samples that you probably, run the k-means algorithm through probably can give you a little bit of an edge there too. If you're going to run it more times, perhaps it'll help.
Yeah, but you can see where k-means good up in cell number 96. K-means good is given an initial guess, whereas k-means bad is not given an initial guess, so that it's left to its own devices. It will just randomly initialize and go from there.
So here's the question. The question is, if you give it a bad initial guess, is it going to hurt you or help you? Your initial guess is, you have to kind of, you have to hope that you're going to give it a decent guess. Like, for example, let's see, if I were to say this is negative 1.5 and 2.5 that they're giving the initial guess on. So let's change this to.
You can round it off to integers and then see what it does. Pretty robust.
Yeah. So maybe it's less dependent upon the initial guess, as long as you give one.
As long as you give a reasonable one, right?
A reasonable one, yeah.
Yeah. I mean, if you switch the signs on all of the x and y coordinates, I'll bet that would be an interesting experiment. Then you'll throw it all. Then you give it misinformation.
Let's see. Yeah, there we go.
Yep.
so now we're having a plot that's very similar to the other one.
Yeah.
And again, if it's just random, it's luck of the draw. So you can give it an educated guess. Okay, that's good to know. All right. Now, this is kind of like an older computer vision task that he goes through using clustering for image segmentation, where you cluster the colors together, or you cluster the pixels together. It's kind of cool. Thought I ran these beforehand, sorry.
If I can add, so usually from what I remember is that initialization, so usually you would just want them to be far apart. So let's say the first one, you can just pick it anywhere. And then yeah, so the first one, you can just pick it like randomly anywhere. And then the others, you can pick based, like, let's say on a distance as far from the first point. And that way you have this spread out pretty much centroids, which is better than, let's say, than if you would just, let it randomly pick which they may be closer to each other. Does that make sense?
Yeah, that makes sense. But you in here, when we did our additional,
Yeah.
kind of runs, we're still fairly far apart from each other here.
Yeah.
We have one in the center. We have, one, at 2, -2, one at -3, 0, and we got, this poor result on the third attempt. So I think that, where you start does, make a difference. You do want to spread them out, of course, but I think that,
Right.
it also is kind of, it's kind of like, if you have an idea of where it is, you should try to, maybe you can try to hone down, where you want it to put that initial possibility. But if you don't, you probably are better off random.
Yeah. Cool.
All right. So what he talks about is a dimension reduction technique here. And he is taking the, see if I can get this a little bigger for you. He's taking the different pixels and the different, colors that are present and kind of squashing them down. So the original image on the left, you can see, multiple different shades of, orange and yellow and green and some, brown orange in the background there, and then the bright red ladybug. So going to 10 colors from, pretty much infinite, there's not really a tremendous difference, although you do lose some of the oranges that are present in the center of the dandelion. Going to 8, now you're starting to lose the redness of the ladybug. And going to 6, you lose the center of the dandelion. 4, the ladybug is pretty much forced into being green. And 2, you get this kind of abstract, it's not a black and white, but it's a green and yellow, where everything is either green or yellow and kind of just blurred out or spread out. So he's running this by clustering it at progressively lower k-means. And I thought that this is kind of cute. It's just, I think it's more of a good example of dimensionality reduction, applied into the, the image space than actual segmentation in the space that we're actually trying to segment the image into, flower or ladybug. But you have to have at least 8 colors, probably 10, to really capture the reds that make up the ladybug. Let me see what else he said. Yeah, and because the k-means algorithm prefers clusters of similar sizes, it'll tend to kind of wash out the ladybug because it's a small cluster of similar color, as opposed to the larger clusters of similar color in the dandelion and the grass. Cool. Questions? I don't really know what else to say about that. So So now we're going to go through the digits data set and try to cluster that. Huh. And he trains first the logistic. So basically, he loads the digit data sets. You have I believe the numbers and labels here. We split it into a training and test set with train test split. I think he's splitting it randomly, or he's setting the random state for the split to there. And I think it's a 50-50 split in train test split if he doesn't do anything else. So he fits a logistic regression model using the LBFGS solver. Fit it with X train, Y train, so you're passing your data and your labels. And you get that. So the logistic regression score for the test set with the test labels is 96.8%. So you can basically get 97% accuracy just with a linear, linear regressor. So the question is can we do better by using k-means as a preprocessor? So he decides to cluster the training set into 50 clusters and replaces the images with the distances to the clusters and then apply a logistic regression model. So import the pipeline. The pipeline is the k-means and then the logistic regression. Test the pipeline. We train the pipeline by fitting it on X train and Y train, data and labels. And then we test it on our test data set. And now we're at 98% accuracy. And that's a 28% improvement in error rate. But since the number of clusters of K was an arbitrary choice, he says, well, we can do better. Okay, so let's try to find a good number of K. And he's going to do that by a grid search. And I'm running that right now.
By the way, Stefan, so when he doesn't specify the size like that, like in scikit-learn, usually by default, it gives 25% for the test, and then it does 75% for.
Oh, it is 25-75. It's not 50-50.
Yeah, that's just the default.
Okay. All right. Thanks for correcting me.
A small nit there, Stephen, is your 98 would mean it's about 35.7% because you need to change the 0.97, which is what he got versus, yeah, even I got 0.98 when you run it now. So you need to change in that equation the 0.9777 to 0.98.
Okay.
So
unfortunately, my Colab is stuck in the grid search.
yeah.
I think this.
So I have a question.
Recall, this took a while, didn't it? Because I ran this once a few days ago, but I think that this is because they're going to 100 clusters.
Yep, takes a while.
Yeah, it's going to be a while. Sorry, I thought I ran this whole notebook beforehand, but I switched it to light because it's really hard to see it on the axes on the dark. I was trying to fool around with matplotlib so you guys could see it, but I couldn't get it to the Colab parameters were hard to override. So I think it kind of reset things. So I apologize for that. So he's doing a grid search, and this is going to be a while.
So I have a question while we're waiting.
Yep.
Trying to understand why it gets a better score. I mean, what's he doing differently? Are the cluster numbers now, are the cluster assignments now being added to the label? Is that what's going on here?
I gotta be honest with you.
It's
I think this is kind of, I don't think this is particularly rigorous, because what I think you're essentially doing here is, I think you're kind of feature engineering in a way. And he kind of addresses that in the future. And I think that one of the things he does to address it, I think, is very useful and valuable. I want to bring it up. But the thing is that if you think about it, right, you have a data set of digits. You have 0 through 9, and you have, let's say you have 2,000 different digits, okay? I think that's about that is present in the data set. If you were to assign each of those, if your n was 2,000, okay, like the k-means, then each image would kind of be its own cluster, you know? So it's kind of like you're trying to get to memorize the exact configuration of those individual clusters, not necessarily, you know, not necessarily trying to divide it into clusters that are similar. So with this, what he's doing, it appears that as the number of clusters go up, you know, your accuracy improves. And I didn't get to a point where it started going down afterwards, but it seems kind of like a hack. You want to try to get it as few clusters as possible, but you know, you can just increase the number of clusters and it works better.
right. But scikit-learn is so slick, you know, it's pipeline formalism. It's so slick that if you just look at the code, you don't really, at least I don't really have a good feeling for what's going on. My guess is that it's adding the cluster assignments as features, and that, and as you said, feature engineering, and that those additional features are helping it to do a better job of classification. But I can't prove what I think. I can't prove my conjecture because I don't see where it is actually being added, where they're actually being added as features. Do you see what I'm saying? It's just that scikit-learn is so slick that you don't, you know, you look at that statement, the pipeline statement, and you don't really get a good feeling for what it's doing.
Well, yeah, I mean, you know, how would we figure it out? I mean,
probably try to do the same thing manually. You know, in other words, write code to do the same thing without using the pipeline feature.
Yeah, I mean, I'm just kind of drawing on my own experience with similar, you know, attempts to do similar things. And, you know, you can kind of on paper, you start, you know, you want your network to perform better. Okay, make it deeper. You know, or make it wider, you know, but you can just end up memorizing.
Well, but in this case, it's doing.
In this case, it's not because
it's not memorizing because it's doing it's reporting a validation score. So
right, but since it's really kind of, your clusters are getting more granular, you know, in a sense you kind of are kind of memorizing. There's going to be a sweet spot at some point, you know. If you pass that point, it's going to do worse, you know. It's the whole you know, bias variance trade-off, you know, thing all again. But you know, I think that in terms of kind of what it's doing, you know, it's kind of, you know, you can improve things by adding more clusters and making the clusters more focused and granular rather than broad, you know. But you know, time after time when we do things like that, you know, we see that when we introduce new or out of sample data, these algorithms tend to fail because they're presented with something that is, out of sample, or they're presented with something that, they were over optimized, or curve fit on. It's not exactly the same thing, but it's kind of the same thing. It's the same problem that we run into again and again, I think. Let's see if we're done. We're at 55, 57. So now if I was smart, I would have put in the NVIDIA rapids, sorry. And we would have not had spent all this time here. So, but I wasn't. While we're waiting for that to do, let's take a look back at the text. So, he brings up that point. Since there are 10 different digits, it's tempting to set the number of clusters to 10. However, each digit can be written several different ways. So it's preferable to use a larger number of clusters, such as 50. I think it's preferable to use 100 or 200. So, what he says here, okay, so let's find a good value for K using this grid search technique from 2 to 100. And when I ran this, I'm pretty sure that, he said, okay, well, K99 clusters, we get the best accuracy boost at 98.22. And I kind of looked at that and I said, yeah, I can keep running that and keep getting more accuracy. And that's what he says. You may want to keep exploring higher values for K. So at some point, I'm sure it's going to taper off, probably when it gets to around, I don't know, 300, 400, 500, but I don't have the interest in running that. I'm sure most of us don't.
I think this is really interesting because he seems to be adding, the clusters seem to be adding extra information that you didn't have before, and that's why it's getting better. I still think that in some way he's adding the cluster assignment as part of the feature, as a new feature, so that now, instead of just having the pixel values, of all of the, whatever it is, 784 pixels, now you have those 784 features plus the 50 or 99 clusters, cluster assignments. And that's why it's getting better. That's what I think.
Yeah, I think so too. I think it's, I have a dim view when when you optimize and your optimization works at the end of your range, it's kind of a good indication that, your optimization is actually, you could continue your optimization and do better. So we know that the answer is 98. I'm going to stop this, not that we belabor the point.
Interestingly, when I ran it, it's actually optimized at 57, and I got a score of 0.98 at 57 rather than at 98 or 99. And in fact, it dropped when you went above that.
Really? Did you change any of the the random states or anything like that?
Not that I recall, no.
Okay, cool. Did you run your home PC or did you run it in Colab?
Colab.
Really? Okay. That's interesting.
I was kind of surprised by that. And so my results didn't match what he says later because it kind of went up and down as we were discussing it. Drops after a point.
Yeah, no, I would expect it to drop after a point.
Yeah.
Interesting. Okay, so let's continue this, and we'll switch to the text for a moment, and then come back to this as the rest runs pretty quickly. So he goes on into using clustering for semi-supervised learning, and I kind of like what he starts talking about here. This is, I thought this was kind of good, and I think I've done similar things, but I've not done it as rigorously. And I think that he's a good approach to it that we should pay attention to. So he he first starts training a logistic regression model on 50 samples from the data set, okay? He checks his test set and gets an 83% accuracy, okay? And then he clusters the training set into 50 clusters. So he's going to find the image closest to the centroid and call these images the representative images. So what he does is his K is 50, the K-means of 50, okay, 50 clusters, and he fit transforms the training set. He takes this representative index and he gets the representative digits of X train. So these are the 50 representative digits, okay? We evidently have to manually label it as the output. But each one is like the best example of that cluster. It may not necessarily be what we think is the best example of that cluster, but it's what that cluster has said is the best example of it. And so now he's going to use those 50 labeled images and see if the performance is better. And he actually gets a substantial boost in performance of 92% with those 50 labeled instances. So what I think is cool about this, and I think it's notable, I think and it's worth paying attention here, is that number one, okay, you're working with a very small number of samples. And, you know, for a lot of the applications that we have, getting, you know, extensive data is problematic. And so sometimes you're forced to work with small data sets, you know, 50, 100, 200, okay? You don't get necessarily the million or 2 million or 5 million data points. So if you have a representative data set with those, you know, with that small sample, you're in a very different place than if you just are taking all comers. And this is something that has been taught to me by a really smart guy who is one of the few people I think that really knows what they're doing in something called synthetic data. So it is you know, this is a part of data engineering that's worth paying attention to. So, you know, labeling those representative instances, we can go one better now, and then we can propagate the labels to all the other instances by label propagation. Let's say we have our representative instances, okay? We have our data, all right? Let's go back and relabel the data with those representative instances so that we get the best segmentation or the best separation from the centroids that we can. And you can do that obviously in other different ways as well. So he's going to iterate over the clusters, okay, and train the model again, and now it gets up to 93%, which I thought was pretty good. So what he says the problem is with that is that each representative instance's label were propagated to all the instances in the same cluster, including the instances that were close to the boundaries, which are more likely to be mislabeled. So let's see what happens if we only propagate the labels to 20% of the instances that are closest to the centroids. So if you can imagine the centroid, let me switch back to this. So you have, in our original, you have these 5 centroids, okay? So if you can imagine the area of the centroid and the area of this centroid, and then particularly saying with this centroid, you know something? I'm not going to care about these guys on the outside. I'm going to focus on the inside. And I'm going to exclude this area by saying I only want the 20% closest or whatever percent closest to the centrum of the centroid.
So you're saying let's only label the instances that we're really, really confident of, and let's refrain from labeling the other instances.
Right, exactly. So doing that, come on. Where's my collab? I didn't just close it, did I? No. Never mind, that is my collab. Sorry, I was looking for the book. So by taking, you know, the 20% of the instances and then retraining, we boost the accuracy up to 94%. So, you know, and you can fool around with that. Now, you know, obviously, if you think about those centroids as manifolds, and you say, okay, we're gonna kind of not train on the cases that are peripheral in the manifolds, we're gonna kind of put aside the edge cases. And obviously, you know, we're very interested in the edge cases, but in this particular example, you can get improved accuracy by ignoring the edge cases and focusing on the high probability, you know, representative samples and, you know, propagating those labels. I thought that this was very practical. I really like this. And he calls this part of active, yeah. Mm-hmm.
Strangely, when I did it, it actually gave me better results when I didn't do the narrowing. So, you know, I want other people to try and see whether they can duplicate what he claims, or was it just my specific instance where it did something different? Because my 100% gave a better, meaning when I didn't subselect percentile closest, then it gave me better result. Again, we are talking about fractions. My better result was 0.93 versus when I selected 20%, then it was just 0.9.
I know that, you know, for me, I've gotten variability, you know, in my deep learning algorithms from time to time, you know, in a similar method and a similar manner. My gut feels a lot of times with the scikit-learn and you know, a lot of these mathematical methods, when you set the seed, they're a little bit more stable. I'm not sure why you're getting that variability.
Yeah, that's why I was wondering. I mean, if anybody else,
are you running on a Unix system, or are you running on a Linux system, or are you running
Colab?
You're just running on Colab, right. Colab.
Yep. Yep. So I was surprised by that because I played around with it and reduced it to 40 or 60 or, I mean, the only explanation I could figure out is the original clustering was good enough to where reducing it didn't give it the benefit of only selecting, as Joseph was saying earlier, that 20% means that you're not polluting it with lower probability numbers. But if your clustering is really good, then you ought not to see that much of a difference. So that was the only explanation I could come up with as to why I couldn't see what he claimed to show. But if anybody else is able to duplicate or see what I saw, post in Slack with some possible reasons why.
All right. We finally finished this. So that's interesting. So it actually turns out, similar to what you said, 57 clusters this time
Yeah, that's exactly what I
is
got.
the optimal solution with 98%. Huh. Interesting. Okay. All right. So let's take a look at these that we've been working on, kind of backwards. So these are the representative digits that we've gotten, through applying k-means to the fit transform. You do have to then label them because there are no labels for these representative digits. There's a way to do that.
Stephen, quick question.
Uh-huh.
Quick question. Don't you have to label now these corresponding to what you see?
Yeah.
Or is that not the case? So since, for example, wouldn't you need to label it as 0132764695 rather than what's there?
Oh yeah, I'm looking at it and you're right.
So that's what I did. And then because of that, all my results below changed. So try, see what you get.
Look at that. That is a trip. That's funny.
So Srinivas, while Stephanie's doing that, did you try different percentiles instead of like 20, for example? Did you try like 50 maybe and see what was the
Yes.
what did you?
Yeah, I played around. Yes, I did play around with it. I tried 20, 50, 75, 90. And what I recall, because I didn't save all the results, what I recall is it varied a little bit, but not a whole lot. And it definitely didn't give me a better result at 20 or 40 even, or 10, as it did when I ran it without narrowing the choice, which is obviously the default, which is take everything in the cluster. So I'm kind of curious what Stephen gets when he runs it as well.
I'm clearly too trusting because I would have blown right by that. That's a great pickup. Four. All right, so let's see what happens now. So I get 0.9 performance with my labels. What did he get? He got 0.92 right there. So let's do the label propagation. Now we're up to 0.92. And do the 20 percentile closest. And we go down slightly to 0.897. Srini, I was typing. Did you say that you had you recalled variability in your numbers at 20?
Yeah,
You
and it was lower, just like you're saying.
Okay. So let's say, just for kicks, let's do this. Just 10%. Goes up to 90. Let's do 30.
Yeah, it's higher.
Okay. So it's kind of like, it just, yeah. So maybe it's just, it doesn't like 20 for some reason. But interesting.
His major point of being able to work with 50 and label the others is still very valid, but where I think the variability is only when it constrains the cluster choice. So to your point, Stephen, I think it's still a very significant, important thing to pay attention to because it helps you label unlabeled data and work with small labeled data set. But I think where I saw the variability, and you're seeing it too, is in trying to constrain the choice by giving it 20%, 30% and stuff. That's where his thing seems to not hold, or at least we see different results. But his major point of, hey, with 50 examples, I can give you a labeling of many more examples is still very, very important.
Right. And I think that, like, not to fault him, but, just to share the problem that we all face is that, when you are, creating a random data set, there are other things beside the random seed that you set that go into the creation of that randomness. And you can, actually end up with very kind of different, points or very different randomness than someone else's randomness. You might have even similar levels of randomness, but different, individual points that make up that, and then that kind of gets and bags you. And, I'm sure he's working in an environment, where, his numbers were reproducible, but we are all working on different equipment, and, even the collabs have, changed. There's been advancements in the Unix cores, the packages have been patched, everything. So, I mean, if you want a reproducible result, you have to absolutely, essentially, recreate the conditions that you did, in both software and hardware, to have any hope of, a good reproducible result. Unfortunately, this is a substantial challenge for all of us. All right, so I'm going to switch back to the text. I just want to discuss this active learning paradigm he has. I thought this was kind of neat. Where, look, I mean, the point is true. Domain experts are very expensive to call on. I mean, we had, good Lord, there were 10 of us who spent months labeling a data set. And, each of us were trying to label like 2,000 examples, and it took our lives. I mean, it really took months and months and months. And, it's not easy to do. So, or it's expensive. You have to pay people a ton of money. So the smart way of doing it, okay, is that you gather your data, okay, you take the model that is trained on what label instances that you have, okay, and predict on the unlabeled instances. So then take the instances which are lowest probability and most uncertain, and then give those to the expert to be labeled. And then take that data, give it back to the algorithm, and iterate until, you know, it's not worth doing anymore, or you run out of money, or so forth and so on. But I think that this is actually a very intelligent way of doing it, because your easy stuff you grab quickly, right? And then you don't focus a lot of time on the in-between stuff. You try to short circuit that by going directly to the edge cases, filling in the edge or the periphery of the cluster, if you will, okay? Defining that, and then you can just kind of capture everything that's central to it more easily. And then, you know, the next edge cases are what you kind of address. All right, so let me switch gears now and talk about dbScan. And the dbScan algorithm is a continuous density region algorithm, which means that as long as you have, you know, similar densities, you're good. If the densities start to peter out, it will do less well. So for example, the dbScan will do well on a cluster like this and less well on something like this. So the algorithm counts how many instances are located within a small error, an epsilon distance from it. And that's called the epsilon neighborhood. If it has at least a minimum number of samples of instances in its epsilon neighborhood, then it's considered a core instance and is located in a dense region. All the instances in the neighborhood of a core instance belong to the same cluster. And the core instances can stack, so multiple core instances may form a single cluster. An instance that is not a core instance and does not have one in its neighborhood is considered an anomaly or an outlier. So basically, for you to be a core instance, you have to have more than, you know, x nearest or k nearest neighbors that are close by within the epsilon distance. Others will have less than that k nearest neighbor, but more than 0 neighbors. And if it's just hanging off on its own, well, it's hanging off on its own and it's considered an anomaly. So dbScan, you can import it, and they use this Moon data set and give it labels. So they fit it with the dbScan algorithm with an epsilon value of 0.05 and 5 minimum samples, and they fit it. So let's take a look at the code. Load it in, make the moons, do dbScan. Here are the labels for dbScan with the .labels object. So each of these different numbers are a grouping, except for -1 and 0. I think, if I recall, the -1 is the anomaly. This is how many samples you have, 800. These are the core indices that are the core samples. Label 4, 5, 6, 7, 8, 10, 11, 12, 13. Forget what these components are. These are the core. These are the coordinates of the core instances that are expressed. So negative 0.02 and 0.4. So it's expressed as an array. He reruns it with an epsilon neighborhood of 0.2. Oops. And he plots it. So these are these moons, and the different groupings, I believe, are the different colors here. And those X's, I think, are the anomalies. So when the neighborhood is 0.05, now if you increase the epsilon neighborhood to 0.2, all of a sudden you get this nice big band of density sucking up everything. They're all pretty much the same instance. These are all the same, and these are all the same. And it seems to work better. The question is, you know, which would you rather have? I mean, out of curiosity, let's do it with 0.1. Oops. And we should see something kind of in between. So this is going to be 0.1 now. And 0.1 is pretty good, but we still get one anomalous data point over here. So he imports a k-nearest neighbors classifier. So this was kind of strange. All right. So on page 257, he discusses how dbScan does not have a predict method. It has a fit predict, but you can't predict it. And the way around it is you go into k-nearest neighbors. And the rationale for this is, hang on, dbScan, no predict. Okay, so the rationale for this has been shown on Stack Overflow. And basically, dbScan, the way it works is the clustering is somewhat destructive. So if you were to put in a new point, it would change all the clusters in terms of calculation. So the way around that is to use this KNN method that he discusses. Any questions about that quickly before I move on? Because when you put the new data point in, it's going to change the distance to a cluster, and therefore it'll alter what you did. So you can't just run the predict method.
So the concept is that you use k-nearest neighbors to identify the nearest neighboring cluster to the new point that you provide without disturbing the clustering of dbScan. Is that a right summary
Yeah, I believe
of
so.
what he's doing by this?
Yes, yes. That makes sense to me.
Okay, thanks.
All right. So where's my am I showing you my Colab screen or am I showing you the book right now? I want to be showing you it's the book. I want to be on the Colab screen.
You see the book.
There we go. Okay, so we import KNN, okay, choose 50 neighbors, and we're going to fit the KNN with the components and the labels of the dbScan, okay? And then we're going to pass new items, new points, and allow KNN to predict those. So for each of these points, it predicts it'll be part of the first, rather the second group, the first group, the second group, the first group. And these are the prediction probabilities. Or actually, these are the predicted points for these points. I think it makes a little bit more sense just on the figure. Good. So you can use the KNN to create a decision boundary, and the plotted points lie either in or outside of the moon clusters, and basically you can do a classification, A versus B there. And here he's predicting that the first point is an anomaly because it lies out. Second point is part of cluster 0. Third point is part of cluster 1. And the fourth point is an anomaly. So I thought that that was kind of cool, actually. And I think that this is where we are going to stop for today.
You know, one thing I was just wondering, now if he mentioned at any point, like feature scaling, like, so for example, k-means, yeah, we would do feature scaling, and for dbScan, I'm trying to see the, did he mention anything about, to just double check, you know, because like we said the epsilon here, right? So so I'm just thinking now if feature scaling would still be, you know, feature scaling is always recommended in a way, even
Right.
for screen. So for dbScan, what's the logic?
I think if you didn't have feature scaling, then you wouldn't have you might not have, well, your epsilon choice would be a problem, right? If every direction has the same scale, then epsilon means the same thing in every direction. But if you don't scale, then epsilon might mean something different in one direction than in the other, you know, if the scales are different.
Yep. Okay.
Yeah, and also if you look at the pictures, you know, that he's doing with the half moons, you know, he's doing them from like kind of like -1 to 2. I mean, he's still staying fairly close, you know, to a -1 to 1 kind of distribution. It's not perfect, but you know, I think that, yeah, I think that feature scaling, you know, would be indicated, and especially if you're, you know, getting outside of the, you know, -1 to 1, you know, probability range.
Yeah, makes sense. Cool. Thanks.
I had a thought. I wanted to just go back for a moment, if I may, back to the MNIST digits example where he did k-means and then he put it through the logistic regression. Or sorry, was it logistic or linear? Logistic.
It was
regression.
logistic.
Yes, yes. I originally was speculating that he was adding the k-means cluster assignments as features to the already present pixel values, but I now think that he's substituting, instead of getting the information from the 28 by 28 array of the image, he's substituting the information of the cluster assignments. And that's interesting to me, that in other words, going to a different representation of the information gives a better result.
The other thing, Joseph, is this is grayscale MNIST. It's not 28 by 28. And the number of images are much smaller. That was something that threw me for a loop initially too. It's not the regular MNIST. It's a grayscale MNIST with only 1,800 images and only grayscale, is my recollection.
No, I mean, they're still 28 by 28 pixels, right?
Yeah, probably.
The individual images, right? So they have 700. They have dimensionality 784. But now he's in a sense reducing the dimensionality from 784 to either 50 or 99 when he does the cluster assignments. And with that reduced dimensionality, he's getting better results than were gotten from the full 784 dimensional data. That's just really interesting to me.
Yeah. So that's why he goes for 50 rather than just 10 dimensions in a sense.
Yeah, maybe 10. And maybe 10 is just too few to get a good result.
Right. Right.
Why is that saying?
Based on what we saw with PCA, 154 ought to give us the best.
Interesting. But did PCA didn't give better results than the full image though, right? In other words, by using the full 728 pixels.
Better. Oh yeah.
It wasn't better.
But I thought, yeah, no, I don't think it was better.
So this is a case, right? It was faster, but this is a case where we have dimensionality reduction that actually leads to better results. That's just really mind-blowing.
Okay, not gonna let me do that. So let's just type it out.
Yeah, so, and 50 here is actually shown 57 gives you better than 99, right? We saw that.
Yeah.
But I guess it's the combination of the classifier, meaning logistic regression, and so if you use a different, say, SVM, and maybe the clustering number would be different too. But you're right. I mean, it's a lot less dimensions than the 784, and you're getting better results in class.
Yeah, these are 8 by 8 images. So they're like 64 pixels.
Oh, they're only 64 pixels?
Yeah, he says they're 8 by 8.
8 by 8. Oh, okay. Well, still 57 is smaller than 64, so it's still amazing that you get better results with dimensionality reduction.
I think you can do that with small, like something small like that. When you try to do things going larger, they fall apart. So that's why we gravitate toward the deep learning solutions for that. Anyway, cool. All right.
So Stephen, are you sure that it's 8 by 8? Because look on page 253, those representative images, they look awfully better than 8 by 8.
He does say that, Joseph, in the notebook, he says the digits data set, because it's digits rather than MNIST. He loads digits. He doesn't load MNIST. And he said it's an MNIST-like data set, and that's what caught my eye, and Stephen rightly pointed it out. It's only 1,797 grayscale 8 by 8 images.
Okay.
So even the total sample is different.
Yeah, I'm hoping that he's telling the truth. I mean, to my eyes, I think that it's somewhat blurred, you know, because could it be 8 by 8?
Yeah, maybe it's just blurred. Well, anyway, it's interesting. I wonder if a laptop, I wonder if a Colab instance has enough computing power to do the actual MNIST data set. You know, looking for clusters in the 728 dimensional space.
I'm sure.
And I wonder if you'd still get better results with a much lower number of dimensions.
I think you would have to, the number of dimensions would increase, you know, with the larger size of the data set and also the larger pixel size of the MNIST. I mean, I think you could still get a result. I don't think it's going to be a fantastic result. I think it's probably going to be like somewhere in the low 80s, you know. So something fun to do, maybe for the homework session. Does he have that as an assignment? I haven't looked at that. I haven't looked at that yet.
I haven't either.
Yeah. All right. Okay, so I would vote that if anybody doesn't have any more questions or comments, you know, these other clustering algorithms, we'll take a peek at them at the beginning of the next class. I think that, you know, obviously there's lots of different algorithms to choose, and, you know, it's probably better to have a pretty good understanding of one or two, and then be able to, you know, switch when you need to, rather than kind of try to get a weak understanding of all of them. We're going to talk about Gaussian mixtures next time, and it would be lovely hang on a sec. I've put this on my hard drive so I can access it from both Unix and Windows, because I'm zooming in Windows. We have the Bayesian Gaussian mixtures. That'll be fun. And then anomaly detection discussion. So let's try to get through the Gaussian mixtures next time. And perhaps even some of the other stuff. because the collab is, I'm sure, going to be a little bit more extensive. All right, guys, thank you very much. Anything else?
Thanks, Steve. I think you did a great job taking us through this dense material and exploring all the nuances. You didn't skip over anything, so that's terrific.
All right, cool. All right, guys, we'll see you guys on Sunday then. It's 10:30 PST.
10 o'clock.
10 o'clock PST.
Yeah.
Okay, I'll see you guys at 1 o'clock my time.
Sure
Okay.
thing. Thank you.
End of the week.